Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Sonia Olaolo and I'll be walking you through the physics course. Now I want to talk about measurement of heat energy. We'll consider the topics specific heat and thermal capacity, measurement of specific heat. We'll look at latent heat. We'll determine the latent heat of fusion of ice. We'll look at Newton's laws of cooling, consider the melting and freezing points. Then we'll look at evaporation and boiling, after which we'll consider vapor pressure. Alright, let's go. When we talk about heat, we've been talking about heat for a while now, and we've always considered heat as an energy. It is always important to remind you that heat is an energy. It is not the degree of coldness or warmness or hotness of a place or a thing. It is an energy which actually can do work. So, there is what is known as the specific heat. The specific heat is energy required to cause changes in bodies. Now, it depends on what type of specific heat we are considering. We have two major types of specific heats. We have the specific heat capacity and we have the specific latent heat. So, let's start with heat capacity. Heat capacity is the amount of heat required to raise the temperature of a body through 1 degree of Kelvin. Through 1 Kelvin, that's the temperature scale. But when we come to specific heat now, we say specific heat, C, is the amount of heat required to raise the temperature of unit mass of a body, which is 1 kilogram, through 1 Kelvin. So it can be, they have an expression to show this. The expression is that states that MC, the energy involved, that's the specific heat, equals MC T2 minus T1. So T2 minus T1. Now this T2 is the eventual temperature and the T1 is the beginning temperature. So we're talking about change in temperature now. Thus, we can calculate our C by E over M T2 minus T1. Expression E also might be represented with a Q to show quantity of heat, which also, of course, Q M T2 minus T1. Some people do prefer to represent their temperatures not with T, to use the symbol theta. Some prefer to use theta. So I don't know which textbook you might be working with or working from. You might see different representations for the specific heat capacity. A body would continue to change in temperature based on the specific heat capacity and the amount of heat that is supplied to the body. Now, this particular expression tries to bring about, show us the relationship between temperature and heat. It shows us the close relationship that exists between temperature and heat. On the screen right now, you have a table showing different bodies and different specific heat capacities. We have, I'll just mention a few of them. Glass has a specific heat capacity of 670. Aluminium goes with 900. All of them are measured in, of course, joules per kilogram per Kelvin. Water has as high as 4,200. So the unit of specific heat capacity, of course, energy is measured in joules, so that's joules. Mass is measured in kilograms, and temperature is measured in Kelvin. So that gives us our expression in joules per kilogram per Kelvin. It may be expressed in this manner or expressed as joules per kg per Kelvin. So that's the unit for specific heat capacity. I've spoken about specific heat capacity, specific heat and thermal capacity. In a few seconds, some questions will pop up on your screen. Please answer them. We want to know how far you understand what is being taught. Welcome back. Yes. Now we want to consider how we go about the measurement of specific heat capacities and other specific heats of substances. We have different substances and we have a particular method that we do use. On your screen about now, you'll be seeing a particular experimental setup. And on this experimental setup, we'll see, we want to take note of, we want to determine the specific heat capacity of a solid by mixture. So what do? The first thing to do is to put the solid in water. We'll put the solid in water and we heat the water. Of course, we have a thermometer injected into the water. We'll heat the water and we'll take the temperature of the water, which is the temperature at which heat is being transferred to the solid. After a while, we'll take out the solid, of course, using our stirrer or the twine that is attached to the solid, and we'll drop the solid in a container. This container we're talking about this time around is a container that has it's called a calorimeter. The calorimeter has a fillet jet that is it has a protection to avoid the loss of heat to the environment. So it has this fillet around it. Now the metal will be kept inside it and will be allowed to stay. It will allow to stay in the cold water. In the cold water, the temperature of the water will be noted, of course, and the temperature of the water will be noted before and after the experiment. To calculate the specific heat capacity of the solid, the expression above would help us out. While MC talks about everything that has a C in front of it has to do with the calorimeter, while the one with the W goes with water, the one with the B goes with the body that we're trying to calculate the specific heat capacity thereof. So the F means the final temperature, while the 1 indicates the very first temperature, and the 2 talks about the temperature of the metal when it was brought to the calorimeter. Now the temperature of the metal when it was being brought to the calorimeter would be the temperature of the water when it was the temperature of the body when it was being brought to the calorimeter will be the temperature of the water after it was heated. That is I said the setup. We'll first take the metal, we'll put it in water, we'll heat the water to a certain degree, and we'll bring out our metal. So that's how we take the measurement. Of course, we stir. We use a stirrer to stir so that the temperature can be uniform in both components. And also, while the metal is inside the calorimeter, we also stir so that the temperature can mix effectively as well. So, using this particular expression, we will be able to calculate the specific heat capacity of the metal. Latent heat. Latent heat has to do with the hidden heat. I remember I said it in one of the lessons that the word latent is of Latin origin and it means hidden. So latent heat talks about hidden heat, that is heat that is being injected or imputed into the system but is not felt or seen in terms of temperature change. When a particular body accepts latent heat, of course, it is not like it's not a kind of special. It's not a special kind of heat that you apply. No, it's normal heat that you apply, but instead of it to bring about a temperature change, rather it will bring about a state of change, a change of state. So when the body is changing states, the temperature remains constant. We have two types of latent heats. We have the latent heat of vaporization, and they have the latent heat of fusion. Latent heat of vaporization is related to evaporation of water or evaporation of liquids. That is, liquid turning to gas or gas turning to liquid. While latent heat of fusion is related to solidification, a liquid turning into a solid or a solid turning into a liquid, that is solidification or melting, while the other one is related to evaporation or condensation. They are both equal. They are the same. Okay, when we talk about specific latent heat, let's talk about specific latent heat of fusion. Specific latent heat of fusion is the amount of heat that is required to convert 1 kilogram of a solid to its liquid form without a change in temperature. So it is the amount of energy required to convert 1 kilogram of solid to liquid without a change in temperature. So that heat goes in, we have the Q, it goes in, and what comes out, that's mL. So L is calculated by Q over M. Whether it is specific latent heat of fusion or specific latent heat of vaporization, the formula remains the same. The only difference between them is vaporization is for vapor, it's for liquid and gas, as in the relationship between liquid and gas, while fusion is the relationship between liquid and solid. Let's consider the determination of the latent heat of fusion in ice. To determine the latent heat of fusion of ice, the experimental setup on your screen would be used. From the experimental setup, we can see that ice is being put in a calorimeter, and there is also water in the calorimeter. Of course, the calorimeter, as usual, has a fillet jet where we store cottons to prevent heat losses, to minimize heat loss, and of course a thermometer which is taking measurement of temperature. We also have the whole thing being placed on a weighing balance. The first thing we take is the weight of the empty weighing balance. Then the next thing we take is the weight of the calorimeter. I said empty weighing balance. The first thing we take is the weight of the empty calorimeter. The next thing we take is the weight of the calorimeter and water. After which we weigh the calorimeter, the water, and the ice which we would want to. So all this, the idea is we want to find out what is the temperature, what is the weight of each of the components, instead of us carrying our water and trying to weigh it on its own. After taking all these weight measurements, these weight measurements are very important. Then we start taking temperature measurements as well. The temperature of warm water, that is the temperature of the water that will be used to melt the ice, that is about to be used to melt the ice, and also the temperature of the water after all the ice has been melted. That would also be taken note of. The C, and we're going to need to know the specific heat capacity of the calorimeter and specific heat capacity of water. So how does this experiment work? When the ice is being put inside the warm water may be as low as 25 degrees Celsius, or maybe it may even be your tap water. Of course, you know when you put ice in your tap water, the ice will dissolve. So that is what we are expecting to happen. Only that we don't want it to dissolve and heat that we do not know would just get lost. We want to be able to monitor the entire heat process. So that's why we are putting it in a calorimeter, and we are putting a lid over the entire setup. Now, when the setup everything is placed in place, the first thing you notice is that the temperature would begin to fall. The temperature of the setup would continually fall, and to get to a particular temperature which is the final temperature. At this final temperature, all the ice would have melted. After the ice has melted, then the body would want to begin to regain temperature, probably from the calorimeter or the environment. So we'll stop the experiment at that point. We note the lowest temperature. The formula expression on the board shows the formula to calculate the latent heat of fusion of ice or the ice. The experimental setup. The first thing we put into consideration is the heat capacity of the calorimeter, which is the mass of the calorimeter multiplied by the specific heat capacity of the calorimeter, which would be also multiplied by the temperature difference, that is the amount of temperature that goes to the calorimeter, plus the amount of temperature that goes to the calorimeter is the same amount of temperature that also goes to the water. That's why they have been added together before multiplied with the temperature change. So, plus the temperature, the mass of water, that's mass of the calorimeter with water minus mass of the calorimeter alone, and multiplied by the specific heat capacity of water. So when you add that together, that gives us prepares us for specific heat capacity, and you multiply that with temperature difference. This is the temperature before when you start the experiment, and this is the temperature at the end of the experiment. Now minus the temperature of the volume of ice. This is the volume of ice, and of course, when the ice would have completed, when it would have completely melted, it would be in liquid form. So it will have a specific heat capacity of its own too, and it will be at the temperature of the final. So that expression is supposed to give us the difference of this expression is supposed to give us what the energy provided to the ice. This is the energy provided to the ice from the calorimeter, energy provided to the ice from the water. That's these two. All of this, that's what comes there. Then this is the energy received by the water, which is formed from the ice. So the remaining energy, which is not accounted for, because there will still be some energy, but it is not its losses. It's not an its loss. So the remaining energy is the energy that is required to convert the ice to water. That's why when you throw your ice cubes into water, you don't get your water to remain at the same temperature even after your ice has melted. When your ice melts, the water becomes chilly, becomes very cold. It has lost some of the heat it used to have. It has lost it to breaking the ice down into water. So the specific latent heat is also calculated in joule per kilogram, which can be either represented as J over kg or as J kg raised power minus 1. In similar manner, we can conduct an identical experiment for vaporization. The difference would be, instead of us putting into consideration ice, we would consider trying to boil water, and we'll try to boil the water probably using an heat source, electrical heat source. Using an electrical heat source would be a very good idea, because you can actually measure the amount of electricity going into the system simply by noting electrical power consumed. So it states that when there is a small temperature change between a body and a small difference between the temperature of a body and the environment, the rate of change, the rate of heat gain or heat loss is proportional to the change in temperature, that's the difference in temperature between the two bodies. For example, in the kitchen, I like to use the kitchen to do an illustration because many of us can relate to it. In the kitchen, you go there to pick your food. Your mom dished your rice into the plate. The temperature of your rice when it was freshly dished is very high. But because of the ventilation of the kitchen, you notice that the temperature of your food before you finish eating would have reduced greatly. Yes, that is Newton's law of cooling coming to play. Because the temperature inside your room is much lower than the temperature of the food, it is being lost from the food and gained by the environment. That's why when you are drinking tea from your mug, when you carry your mug, you feel the temperature of your mug. If your tea is a hot tea, the body of your mug will be hot, even after the tea has been finished. And if your tea was a cold tea, ice cold tea, the temperature of your mug will be cold, even after the tea has been finished, because it was lost to heat. And the mug itself would have to lose the heat that it has accepted from the liquid which was in it at one time to the environment, which is the reason why if you should leave that mug for another maybe 5 to 10 minutes, it would have cooled back to the normal temperature. The same thing happens to other substances, but the rate at which they cool differ from one to another. And that's one of the reasons why we have to study what is called cooling curves. Cooling curves are pre-designed graphs that show how substances react to heat, how substances accept and expel heat from their systems. Well, most of these substances, the reason the relationship between the heat they retain, the duration for which they can retain their heat, is very, very much connected to what we have been looking at earlier, which is a specific heat capacity. A body that has a high specific heat capacity has the chance of retaining the heat much longer than ones with lower specific heat capacities. Melting and freezing points. It has been noted that most materials that we have around do melt at the same boiling point, the same melting, the same freezing point. The temperature at which the body freezes is the same temperature at which it would melt. But it is not all substances that do react like this. Some substances do have a range of melting points, especially impure substances. Substances that contain different kinds of materials in them, compounds that contain mixtures. Let me put it that way. That contains mixtures. Like, for example, when you go for your alcohol, your beer that you buy, your beer will not freeze at one specific temperature because it contains a couple of compounds in it. Now, each of those compounds would freeze at its own time. The temperature at which it would freeze may be within a particular range. That is, the first component of the beer might freeze at about 3 degrees Celsius, while the next one freeze around 0 degrees Celsius, and it might take as long as maybe minus 7 degrees Celsius to freeze the last component of the beer, assuming that it just contains just 3 components. So this particular freezing points, when you keep checking the temperature of the body, you notice that the body is thickening, it is freezing, but the temperature is still changing. Well, it is due to the composition of several components in it. And we have some particular components actually which do not go through the liquid states, which go from solid straight to gas in a process called sublimation. Evaporation and boiling. Many times, most of us actually do mix up evaporation and boiling. We don't know the difference between them. The truth is, most of the time that we see these events occur, they happen hand in hand, they work pari passu. You see both of them take place, one and the other almost immediately following it. One accompanies the other. What is evaporation? Evaporation is simply the conversion of a liquid from its liquid state to gas. Sometimes evaporation can occur even without boiling. For example, when you sweat, when you run and you sweat, and after a while you stand, you see in a few moments the sweat on your body disappears. That's evaporation. But you do not see any boiling because the temperature of the environment is definitely not up to 100 degrees. And water boils at 100 degrees. And what comes out of your body is water. So evaporation can actually occur without boiling. Same thing, if you put water on a table and you turn on the fan, lock the windows, pour a little water on the table, turn on the fan, and lock the windows. As the fan is blowing the cool breeze on the water, it would disappear. That is evaporation taking place. So evaporation does not necessarily have to be a process that accompanies boiling. Evaporation has very many benefits. Evaporation is dependent on 5 basic things. First is the temperature of the location. If the temperature is high, evaporation will occur at a higher rate. Another thing again that evaporation depends on is the quantity of moisture in the air. Quantity of moisture in the air. As a matter of fact, if the air is very moist, there is a chance that instead of evaporation to occur, condensation would occur unless the temperature of the location is increased. This is how our rain actually is created. Water is evaporated from the seas, from the roads, from different locations, and it goes up to the sky, forming clouds. And when it gets to a certain height, altitude, the cloud is cooled and condensation happens and there is precipitation. That's water droplets start pouring. So rain is created. Also, evaporation is dependent on pressure. The amount of pressure acting on a particular substance controls whether evaporation will occur or not. If pressure is high, evaporation is low. When pressure is low, evaporation is high. Surface area of exposure is another feature which evaporation is dependent on. When something is exposed to a large surface area, there is a chance of high evaporation. That is just like when you keep a bowl of water on your table and you leave it all day long. You'll find your bowl of water there. When you keep a cup of water on your table and you keep it all day long, you find it there. But if you pour that cup of water across a table, a very big table, and you leave it there, by the time you come back, you will not see any trace of the water on the floor, but most of the water would have gone, if not all. So that is large surface area. It encourages evaporation. The last component to consider in evaporation is temperature. Evaporation increases with temperature increase, and evaporation can occur at any given temperature, as earlier stated. Talking about boiling, boiling occurs at specific temperatures. Boiling does not occur at any temperature. It occurs at specific temperature or specific ranges of temperature for impure substances mostly. So before a liquid can boil, the temperature of the liquid must have been raised to a certain degree. Let's consider the differences between evaporation and boiling. On your screen right now, you'll be looking at a table that is showing the difference between evaporation and boiling. And there we'll see that evaporation is simply change of liquid to vapor at temperatures normally below the boiling point, while boiling is simply change of liquid to vapor at the boiling point. Evaporation occurs at all temperatures, while boiling occurs at given temperatures. Evaporation occurs, but it is not steady. It may occur and cease to occur, maybe because of the air is now become moist or the air has absorbed enough water. But boiling occurs irrespective whether the air has absorbed enough or not, so long as the heat source is present. Evaporation occurs at the surface of the liquid. It occurs at the surface, while boiling occurs in every part of the liquid. That's why from the bottom of the water of the heater, you see the bubbles coming and everything. So those are the major differences between evaporation and boiling. What is the application of evaporation? Evaporation is used in designing of refrigeration and air conditioning systems. Of course, the knowledge is Newton's cooling law applied with the law of with the principles understood. It explains the principles of evaporation. Since there is a change in temperature, one component absorbs heat, while the other one loses the heat. So in your refrigeration system or your air conditioning system, you have your evaporator, which is the one that absorbs the heat from the environment into the air conditioner, while the condenser is the one that loses the heat absorbed by the evaporator to the environment where the heat is unwanted. So this is the knowledge of evaporation that is being used, that is being put to work. Yes, there is no boiling. Boiling does not occur. You don't see your refrigerant boiling, no. But evaporation occurs and heat is being moved from one place to another. Let's consider the kinetic molecular theory in relations to evaporation and melting. In a solid, the particles, according to matter, when we discussed matter, we said the particles of solid are closely packed, they are stacked on each other. Well, when melting occurs, the heat received increases the kinetic energy within the molecules, thereby more vibration occurs. And as vibration increases, as the vibration occurs more frequently due to the high kinetic energy which has been possessed, the solid begins to change its form and starts being a solid and becomes a liquid. In the liquid, we know that there is more kinetic energy being used up. The molecules of liquids are in a more freer motion compared to the solids. The molecules of the liquids are in freer motion compared to solids. So when heat is supplied to a body, when the body gains energy in form of heat, it increases the kinetic energy of the molecules of the substance. Thereby, the molecules develop a higher kinetic energy, which means higher velocity for them. Thereby, they move more randomly, more freely, which is a nature of the liquid state of substances. The same thing occurs for gases. The molecules of the substance begin to move. That's at evaporation, rather. The molecules of substance begin to move at even a greater, higher degree of freedom. At this greater, higher degree of freedom, the substance begin to lose the bonds that are binding the substance together, preventing it from being free radicals, begin to break. And that's one of the reasons why you see that when your water is boiling, the bubbles come from the bottom where the heat is being supplied. If the heat is being supplied from the side, you see that it is from that particular side that the bubbles would come from. Anywhere the heat is supplied from, the bubbles will come from there. It's at that point in time, the molecules that are directly in contact with the source of heat get so much kinetic energy and they want to fly out of the body. So you see the bubble coming from the bottom of the pot to the surface of the pot, and then it bursts open and vapor comes out of the whole setup. Kinetic energy is being involved. Vapor pressure. Well, in the past we've talked about pressure. Let me first test one or two things about vapor. We all know what vapor is. Vapor is a liquid which is being converted into a gas. That is the gas form of a liquid. Now, vapor pressure, in this particular context, we are talking about water vapor pressure. That's the pressure of water vapor. It is one of the features or the things that we consider when we're considering atmospheric elements of weather. It is one of the elements of weather, and it is one of those things that we use also in the design of our cooling systems. Yes, it has a lot of applications in our day-to-day lives. But let's look at it from the sense of what it really is. Vapor pressure actually talks about the quantity of water or moisture that is present in air. The quantity of moisture that is present in air. Now, pressure itself is amount of force acting per unit area, but a vapor always has its own pressure in air. There is a law that when it comes to gas laws, we'll come across Pascal's law of partial pressure, where he talked about every pressure adding together, many different pressures coming together to form a very big pressure. Now, the water vapor itself has a pressure of its own, which combines with the other components of air, such as dust, as oxygen, nitrogen, the rare gases, the carbon dioxide. All of them have their individual proportional pressures with which they merge together. Now, in a particular room that is moist, there is a pressure, if a room is moist, the amount of water vapor in that air is high. Therefore, it will possess a high vapor pressure. And also, when harmattan season comes, the air that is blowing around is very dry, which suggests that there is low water vapor at that particular time. So you see one of the applications of water vapor pressure in our day-to-day lives. We can calculate vapor pressure by we can estimate the amount of vapor pressure available in air by simply trapping the air and subjecting it, measuring it against the atmospheric pressure. We can also calculate the amount of pressure possessed by a particular air. Of course, every gas, when it is stored in a particular container, possesses a pressure of its own. So for you to calculate the pressure of a particular vapor in relation to air, it means you will have trapped that particular vapor in a container. And then you can now set it up in your, using your, what's it called? Your manometer or a laboratory barometer, working on pressures. Let's talk about saturated vapor pressure. A vapor it can be said to be saturated or unsaturated. When we say something is saturated, it means it has accommodated the maximum it can possibly accommodate, and any addition you try to make would simply result in the thing coming out. I'll give an illustration. Get a bowl of water, or maybe a glass of water, a small glass of water. Add a tablespoon of salt. When you stir it together, you notice that the salt would completely dissolve. I'll advise you, when you want to do this kind of experiment, you can buy maybe 15 naira salt and you can use it. Just keep adding the salt and keep adding the salt. It will get to a point, the salt would no longer dissolve completely. At the bottom of your drink, of the water, you'll find some salt particles there. It tells us at that particular point in time, the water is saturated with salt. It can no longer accommodate any salt. So the saturated vapor pressure is saturated vapor is a vapor that is filled completely with moisture, that it can no longer hold any more of that moisture. Any additional moisture being added to it will simply result into it sending out some of the moisture content which it already had. So it will result to the precipitation of the moisture. And this is one of the concepts and principles behind rainfall. So we understanding the atmospheric vapor pressure actually can help us to predict when rain would fall or not. Also, this vapor pressure is dependent on a couple of factors. Factors like pressure, atmospheric pressure, factors like altitude, that is height above the earth, factors like height above the sea level, factors like temperature. They all contribute to the amount of vapor that can be held in the air at a particular time. Relating vapor pressure to boiling point. When a liquid is being heated, I'll take example of water. When you have your water in a kettle, the water begins to try to boil. But when it gets to the boiling point, the water begins to boil. if your kettle is completely sealed, that is, if it has a cover sealing it up, the water will boil, and after a while, yes, very good example. In your kitchen, when you're cooking, you notice that when you warm your food, especially food which contain water, after heating your food, when you remove the cover and you place the cover down, you find water inside the cover. What you see there happening is simply the water you see there is the residue of the oversaturated vapor which was once inside the pot. When the vapor inside the pot gets so saturated, because of the temperature at the top there, it still stays as a vapor, but immediately you take it off and the temperature of the cover begins to drop. Immediately, all the water vapor that was hiding in the corners of the cover simply begin to precipitate, and then you have droplets of water. So even in boiling, when boiling occurs in a restricted environment, vapor pressure is increased. It can be increased. So we also considered latent heat, that is the heat that it takes to turn a substance from one state to another. That is the heat. It is not felt in terms of temperature change, but it converts the substance from one form to another. We looked at how to calculate how to determine by experiment the latent heat of fusion of ice. We talked about the Newton's law of cooling, which says that when there is a difference in temperature between a body and the surrounding, one of them will lose heat to the other, and the rate at which it will happen is will be based on the difference in temperature between them. We talked about melting and freezing points, particularly mentioning that the freezing and melting points of substances, pure substances, are usually the same, but in certain compounds, a particular thing might have a range of melting points or a range of freezing points. We also talked about evaporation and boiling. We considered the differences between them. Evaporation can happen at any temperature, especially below the boiling point temperature, while boiling point happens at a specific temperature, which is a boiling point temperature. We talked about vapor pressure, we talked about its applications, and we talked about vapor pressure. We define vapor pressure as the pressure exerted by a vapor on the atmosphere. We also took an example as regards heat capacity, specific heat capacity, and specific latent heat. In a few seconds, some questions will be shown on your screen. Please answer them, and if any of them proves to be challenging, you can view the video one more time for clearer understanding.